Welcome to CEDA-Labz. First, let's answer the questions asked in previous tutorial. Our first question was to differentiate continuous assignment statements and procedural assignment statements. Here is the difference. First of all, continuous assignments are associated with data flow modeling, and procedural assignments are associated with behavioral modeling. Left-hand side target in continuous assignment is of net data type, therefore it drives nets. Whereas in procedural assignment statements, left-hand side target is of reg data type, therefore it drives registers. In the former, assign keyword is used, whereas in the latter it is not used. Continuous assignments are defined anywhere within the module. On the other hand, procedural assignments are only defined within structured procedure statements, that is, within initial and always. Continuous assignment statements are best for describing combinational logic, whereas procedural assignments are best for describing sequential logics. The former uses only equals to assignment symbol between left-hand side target and right-hand side expression, whereas latter uses both equals to assignment sign and less than equal to assignment sign and between LHS target and RHS expression. We will be learning this last point in this tutorial as we will move further. Another task was to calculate simulation time for this code. So, the calculated simulation time for this code is 23 time units. In Part B of Behavioral Modeling, we will study delays in behavioral modeling. Also, we will study in detail about blocking and non-blocking procedural assignment statements. Explain conditional statements using if-else and case, understanding looping statements such as while, for, repeat and forever. There are two types of delay in behavioral modeling: intra-statement delay, intra-statement delay. Intra-statement delay is the delay by which a procedural statement's execution is delayed. This delay is provided between the procedural statements. These delays are not synthesizable and are ignored by the synthesis tool. Intra-statement delay is the delay between computing the value of the right-hand side expression and its assignment to the left-hand side. A delay appearing on the right hand of an expression in an assignment statement is an intra-assignment delay. It is the delay by which the right-hand side value is delayed before it is applied to the left-hand side target. The important thing to note about this delay is that the right-hand side expression is evaluated before the delay, then the wait occurs, and then the value is assigned to the left-hand side target. Simulator waveform will remain same for both types of delay. Intra-statement delay is not ignored by synthesis tool. Here is simple example showing difference between the both. In first one, after a delay of 5 time unit A gets its value as B, whereas in intra-statement delay, first RHS variable, B, is stored in a temporary variable, temp, and after a delay of 5 time unit it gets assigned to A. Here is an example of inter-statement delay. Here, second statement execution will start after a 5 time unit of delay. Here is an example of inter-statement delay. In this example, X and Z will be executed at simulation time 0. And second statement, Y equals X plus Z, will also be encountered and evaluated at time 0, but its value will be assigned to Y after 5 time unit of delay. This is the significance of intra-statement delay. Blocking assignments are executed in the order they are specified in a sequential block. As the name suggests, it blocks the execution of the next statement till the current statement is executed completely. Hence, they are order-dependent and sequential in nature. In blocking procedural assignment, assignment operator is an equal to sign. Its syntax is here, which is simply LHS target equals to RHS expression. Non-blocking assignments allow scheduling of assignments without blocking execution of the statements that follow in a sequential block. In a non-blocking procedural assignment, the assignment symbol less than equal to is used. The simulator schedules a non-blocking assignment statement to execute and continues to the next statement in the block without waiting for the non-blocking statement to complete execution. Hence they are concurrent in nature and are order independent. As you can see, syntax is same, only assignment operator is different. Having described the behavior of non-blocking assignments, it is important to understand why they are used in digital design. They are used as a method to model several concurrent data transfers that take place after a common event. Consider the following example where 3 concurrent data transfers take place at the positive edge of clock. At each positive edge of clock, the following sequence takes place for the non-blocking assignments. A read operation is performed on each right-hand side variable, in 1, in 2, in 3 and reg1, at the positive edge of clock. The right-hand side expressions are evaluated, and the results are stored internally in a simulator. The write operations to the left-hand side variables are scheduled to be executed at the time specified by the intra-assignment delay in each assignment, that is, schedule write to reg1 after one time unit, to reg2 at the next negative edge of clock, and to reg3 after one time unit. The write operations are executed at the schedule time steps. The order in which the write operations are executed is not important because the internally stored right-hand side expression values are used to assign to the left-hand side values. For example, note that reg3 is assigned the old value of reg1 that was stored after the read operation, even if the write operation wrote a new value to reg1 before the write operation to reg3 was executed. Thus, the final values of reg1, reg2, and reg3 are not dependent on the order in which the assignments are processed. In example, illustration 1, there is a race condition when blocking statements are used. Either A equals B would be executed before B equals A, or vice versa, depending on the simulator implementation. Thus, values of registers A and B will not be swapped. Instead, both registers will get the same value, previous value of A or B, based on the Verilog simulator implementation. However, non-blocking statements used in illustration 2 eliminate the race condition. At the positive edge of clock, the values of all right-hand side variables are read, and the right-hand side expressions are evaluated and stored in temporary variables. During the write operation, the values stored in the temporary variables are assigned to the left-hand side variables. This example shows how non-blocking assignments, shown in illustration 2, could be emulated using blocking assignments. Initially, values of variable A and B will be read and stored at a temporary location temp A and temp B, and then these stored values will be assigned to the LHS variables. It is important to note that for combinational circuits, we use blocking procedural assignment statement, and for sequential circuit, we use non-blocking procedural assignment statement. Mixing of blocking and non-blocking statements is not recommended within same always block. Difference between both kinds of procedural assignment statements. Execution is sequential in blocking assignments, as they execute in the order they are specified, whereas in non-blocking assignments, execution is parallel as they are order independent. Blocking assignments are preferred for combinational logic, whereas non-blocking assignment statements are preferred for sequential logic. Operator used for blocking procedural assignment is equals to symbol. On the other hand, for non-blocking assignment statement, symbol is less than equal to. Blocking assignment will give same response with both inter-statement delay and intra-statement delay, whereas non-blocking assignment statements will entertain only intra-assignment delay. As its execution is concurrent in nature, inter-statement delay won't have any effect on the statement. I hope it is clear to you. Let's move on further. Conditional statements are used for making decisions based upon certain conditions. These conditions are used to decide whether or not a statement should be executed. There are 2 types of conditional statement in Verilog, if-else and case. and these statements are used in behavioral modeling only, or we can say conditional statements are used within always block only. The expression is evaluated, it is true, the true statement is executed. However, if it is false, that is 0, or ambiguous, that is X, the false statement is executed. Each true statement or false statement can be a single statement or a block of multiple statements. A block must be grouped, typically by using keywords begin and end. A single statement need not be grouped. Nesting is allowed but not recommended. The if-else statement is used to choose which statement should be executed depending on the conditional expression. The if statement can be used in three ways: as a single if statement, as a single if-else statement, or as a multiple if-else if statement, or we can say nested if-else statement. Here is the syntax for all three of them. First one is for single if statement, where no else statement is required. Second one is single if-else statement, with only one if and one else statement. Third syntax represents multiple if-else if statements, where we can have multiple if statements and corresponding else statements. It is a simple example of ALU, showcasing usage of if-else statement. Here we have four cases. When x is 0, 0, y should add the values of a and b. If x is 0, 1, subtraction should be done. If x is 10, multiplication should be done. And if x is 1, 1, division should be done. So, when writing the design code, after all port and data type declarations, we will start with always, and in sensitivity list we will mention all the inputs a, b, and x. Always is followed by begin, and then we will mention these cases via conditional statement. If so, if followed by first condition, x is equal to 2 tick b 0, 0, y should add the values of a and b. Else the second condition, x equals to 2 tick b 0, 1, where a and b must be subtracted. Similarly, third condition and fourth condition. Fourth condition doesn't needs to be mentioned, as it is the only case left. And then begin block is terminated by keyword end, and our module is terminated by end module. Here is the test bench for the ALU example shown in previous slide. Using if-else conditional statement and logical operators, here is the Verilog code of 4:1 multiplexer in behavioral modeling. The same Verilog code of 4:1 multiplexer is modified a bit using concatenation operator. A case statement is a multi-way conditional branch. The case statement compares an expression to a series of cases and executes the statement or statement group associated with the matching case. The case expression is evaluated first. Next, the case item expressions are evaluated and compared in the order given. The set of statements that match the first true condition is executed. Multiple case item expressions can be specified in one branch. These values need not be mutually exclusive. The default case covers all values that are not covered by the case item expressions. Neither the case expression nor the case item expressions need be constant expressions. In a case statement, the x and z values are compared as their literal values. Here is the syntax for the case statement. This is an example of JK flip-flop using case statement. Here is the test bench for the JK flip-flop. As flip-flops are sequential circuits, they will work only when clock is enabled. So, in the test bench environment, we also need to provide clock environment. This is how we generate clock in test bench module. First we initialize clock in initial block via assigning it value 0 or 1 accordingly. Then we generate clock pulse with desired duty cycle under always block. Here is an example of 3:8 decoder. Design block and test bench block for the same is shown here. There are 4 types of looping statements in Verilog: while, for, repeat and forever. The syntax of these loops is very similar to the syntax of loops in the C programming language. All looping statements can appear only inside an always block. Loops may contain delay expressions. The keyword while is used to specify this loop. This loop executes the procedural statement until the specified condition becomes false. If the expression is false to begin with, then the procedural statement is never executed. If the condition is an X or a Z, it is treated as a 0, that is, false. The syntax of this form of loop statement is shown here. Here is an example showing use of while statement. Here a count will be incremented from 0 to 127. The keyword for is used to specify this loop. A for loop statement repeats the execution of the procedural statement a certain number of times. The initial assignment specifies the initial value of the loop index. The condition specifies the condition when loop execution must stop. As long as the condition is true, the statements in the loop are executed. The step assignment specifies the assignment to modify, typically to increment or decrement, the step count. The initialization condition and the incrementing procedural assignment are included in the for loop and do not need to be specified separately. Thus, the for loop provides a more compact loop structure than the while loop. Note, however, that the while loop is more general purpose than the for loop. The for loop cannot be used in place of the while loop in all situations. For loops are generally used when there is a fixed beginning and end to the loop. If the loop is simply looping on a certain condition, it is better to use the while loop. Here is the same example showing use of for loop. The keyword repeat is used for this loop. It executes the procedural statement the specified number of times. Here is the syntax for repeat loop. A repeat construct must contain a number, which can be a constant, a variable or a signal value. However, if the number is a variable or signal value, it is evaluated only when the loop starts and not during the loop execution. If loop count expression is an X or a Z, then the loop count is treated as a 0. The previous example can be expressed with the repeat loop as shown here. The keyword forever is used to express this loop. The loop does not contain any expression and executes forever until the $finish task is encountered. The loop is equivalent to a while loop with an expression that always evaluates to true, for example, while 1. A forever loop can be exited by use of the disable statement. A forever loop is typically used in conjunction with timing control constructs. If timing control constructs are not used, the Verilog simulator would execute this statement infinitely, without advancing simulation time, and the rest of the design would never be executed. Here is an example of forever loop. Here comes the flashback to the story. We studied delays in behavioral modeling, inter-statement delay and intra-statement delay. We introduced procedural assignments in the last tutorial, and here we discussed in detail its two types, that are blocking and non-blocking assignments. Further, we studied if-else and case conditional statements. And lastly, we studied loops in Verilog. And we did some examples. I hope now you may answer these questions.